Yes, Professor Das, is I audible to you?
Yes. Yes, Professor Srivastava, you are. Yes.
Yeah, okay,
Hi.
fine.
Hello.
Just
Yeah,
you
I
can
was not-
share your slides, whatever you want to share,
Okay.
so that
So
we
it
can test. Yeah.
it starts at 2, right? Yeah.
Okay.
Just give me a second. I'll just.
Sure.
I've not used this particular software before. It's a bit apprehensive.
Okay, just share it and then you will get the entire screen.
Right. It says screen. Yes. I got the. This is loading.
Yeah. You will get the entire screen. There are so many options there.
Yes. Okay. So now.
Now click the entire screen and then open your file, whatever.
Yes. So basically, it's showing me everything that is on my screen, and I have to choose the right one. This is what I'm wondering how to do that.
You can click whatever you want only.
Yes.
But before that, you have to open that file on your desktop.
Yes, I have it open, but somehow it's not showing in the list of things. It's maybe I'm just missing it. Give me a second. I'll just.
Okay.
Sir, if it is minimized, then it will not show. Please maximize it, and then using Alt tab, you can shift to this one.
It's actually okay. Maybe I remove everything else from the screen, so that's the only thing. See, what it is doing right now is all my tabs. It's showing all the tabs which are open in my internet, and this. Window. Oh, I got it. Okay. It was my mistake. Just 1 second. Yes. Is this visible now?
Yeah, it's visible.
Okay, great. And is my cursor visible on the screen, or I have to do something special?
Yeah. It's working. It's working.
Oh,
yeah.
Great. Okay.
That's good.
So, okay. So, just yeah. And as I said, I think I'll send you the questions which you requested for, and by evening today for sure.
Sure.
I hope that will be okay.
Okay. We shall wait for 2-3 minutes more because our participants are joining.
Yeah. Sure.
Yeah. Your institute is open now?
Yes, it is. Yes.
Students?
No, not yet. We are not yet open for the students.
Okay.
We sent them back. Last year during the second wave, there was a huge spike, and we were all very worried. And then finally, we decided to send them back. But we got back our 5th year who are doing research projects, and also senior PhD students. Other than that, I think we decided not to get anybody back. But probably after Puja, we are really hopeful that after Puja we will be able to do this.
That's we are also hoping in our institute.
Oh, I see. I see. Probably it's a general thing that after Dashera, it will start. How is the situation there? I mean, your students are on campus or they?
No, we have residential campus. Yeah. But right now, only PhD scholars are permitted.
I see. Not general students.
No.
Once it starts spreading, if one of them gets infected and if it starts spreading, it becomes a big trouble essentially.
Yeah, big trouble. Because hostels are more important.
Yes. For us, we made our guest house a quarantine center, but then once the guest house completely filled up, then I think the institute got very worried, and then we sent everybody back because it went out of control essentially. Yeah. So you guys are operating from home or from office in general?
From office.
From office. I see.
From office. because we are in the campus, and that's the liberty that we can move and
Yes,
go
that's
there.
correct. Yes, I agree.
Programs, computing programs are going on 24 hours around the clock.
Oh, I see.
So we have to monitor all those things also.
Yes.
So we have a
Yes,
supercomputing,
you have.
facility.
I see.
I
And
think
you are
we have-
involved in that. You are involved
Yeah.
in that. I see.
So
Yes, I remember
basically,
IISERK Pune. If you remember, I think maybe 2, 3 weeks back, they had a big fire, which opened up in the institute, and some of their supercomputing facility was destroyed. I think it was very bad.
Oh,
I think it
okay.
started from the chemistry lab, and then it spread all the way. And then I think one of my friends' supercomputer was really affected. I know this personally, so that's how I got to know.
No,
It
we
got
have
very
to be
bad.
very vigilant about our lab.
I
Our
understand.
ACs are running 24/7,
Yes.
one by one,
Yes.
in order to save the supercomputers, whatever we are
Mm,
working.
mm.
Because heating is beyond control.
Yes.
So really, it's very risky to work out on that way.
Yeah, it's very difficult. And particularly
Very
lots of labs are running, particularly the chemistry labs. I think it's very hard time for them to manage.
Yeah.
Because they need some manpower. I think the supervisor cannot just go around all the time manage the lab, right? That's how it's impossible. So I think for some of the chemistry labs, we've had restricted entry for the students. Yeah, this is what I remember.
Okay. So you have been in HRI also, huh?
Yes, I was a PhD student at HRI. I think from 98 end to 2004, I was in HRI. Yeah.
Because
So
I
that's
also did my PhD from Allahabad University.
Oh,
Physics
cool.
department. And I have been listed there HRI.
Yes.
Many times.
Oh, maybe we met. Who knows? We just don't remember. Because our PhD is always submitted in. It used to be. Now the DA University is there, but we got degrees from Allahabad University because HRI couldn't have given us degrees.
Okay.
Yeah, so we had close ties with Allahabad University.
Allahabad. Okay. Fine.
Yeah, recently probably you know that two of our professors from Allahabad, senior professors, they passed away because of COVID. I think one of the ex HODs and his wife both were
Professor Hari Prakash.
Yes, right, Hari Prakash, right, and his wife, I think. Yeah.
Yeah, no, both have gone.
Very sad. Yeah.
Very sad. I know them very personally. Okay.
Yeah. I mean, you have spent your PhD days. I mean, I can. Yeah. I'm sure you are. He's a very kind man. This is what I remember.
Very kind.
Yeah.
And he's also working on quantum computing, a lot of work. And even I have written his name also for this program.
Oh, I didn't know. Oh, how sad.
I have found this FDP from April.
Oh,
so
this is really sad, right? You couldn't have thought that he will be no more by the time this program comes.
Yeah. So anyway, we can start now. I think
Sounds
people
good.
will join later on. Huh?
Yeah.
Okay. Yeah. So very good afternoon to Professor Sorin Das, and welcome to this FDP program on quantum computing from IISERK Gwalior. So Professor Das did his MSc from Department of Physics, Kalyani University, 1998, and did physics PhD from Harish Chandra Research Institute, Allahabad, and now he's working as professor at IISERK, Kolkata. Assistant Professor, Department of Physics and Astrophysics, University of Delhi, 2010-2016. Guest Scientist on sabbatical in Max Planck Institute for Physics of Complex Systems, Dresden, Germany. Postdoctoral Fellow in Zurich, Germany. Research Associate, Indian Institute of Science. Postdoctoral Fellow, Weizmann Institute of Science, Rehoboth, Israel. And graduate student, Harish Chandra Research Institute, Prayagraj, Allahabad. He is also visiting graduate student, Penn State University, USA. And there are so many publications of Professor Das to his credit in different international journals of repute. And his research interest is in quantum condensed matter physics, quantum physics at the mesoscopy scale, topological insulators and superconductors, Majorana fermions, quantum Hall effect, quantum pumps, quantum dots, quantum wires, quantum information and quantum computation, quantum metric and quantum speed limit, quantum measurement, and so on, quantum heat engines. So this is something brief introduction about different kind of awards and honors. He has his ACLED, Institute of Advanced Study Research Residential Fellow from University of Warwick, UK. And he has been a regular associate from ICT, Trieste, Italy, which also I have also there in 1995. That's very good place and institute anyway. And there are so many different publications. I am just observing here a lot of publications of Professor Sorin Das. So thank you very much, sir. And you are
Thank you very
welcome.
much for inviting me.
You are invited to have your talk, start your talk, please.
Thank you. So first of all, let me start by thanking Professor Srivastava for this kind invitation. It's indeed a pleasure. It's every time, many times I have given this refresher course kind of talks in JNU.
Okay.
And actually my wife works in JNU, so I've been involved there giving talks there. And this is the first time probably I'm giving this kind of a talk outside JNU. So yeah, I don't know. I hope you guys get what I try to say. Yeah. So I break my talk into two parts. The first part would be something where, and I will talk about essentially how quantum mechanics is very different than classical mechanics, and how it is when you look at it from the one classical world's perspective, everything about quantum mechanics looks very strange and very unusual. And the whole idea of quantum computation is based on the fact that all these unusual properties, can we harvest them to do quantum to do computation in a much smarter fashion. That's the whole idea of quantum computation. You see, the quantum word comes in because quantum mechanics in a sense is very different than classical mechanics. In the past, all the computers in the past and even at the present times, all the computer which you use essentially uses classical logic and uses classical systems, not just logic. It physically uses a classical system. So essentially, that's equivalent to saying that the desktop or the computer you're using is essentially a classical object. Not completely. I think if you think of the ICs and the way ICs work, if you zoom in, you see there are glimpses of quantum mechanics there. I mean, this discovery of this, the transistors are completely based on quantum physics. But though they are based on quantum physics, they're used in a classical sense. Their quantum power is not really being used to its complete potential. So the idea would be that you have quantum rather than classical algorithms. You have quantum algorithms which you could implement with quantum devices, which work on quantum mechanics explicitly, right? So that's the idea. So I think I will break my talk into two parts. The first part will just be an overview of how quantum mechanics is weird in various possible ways. And the second part will be not really a quantum information or a quantum computation kind of talk. What I will try to tell you about is, in present times, there is this intensive discussion of how to implement these quantum devices and what are the bottlenecks. And one of the primary bottlenecks in really having a quantum computer goes to this fact that if you want quantum mechanics, see, look at the world around you. Nothing looks quantum, right? I mean, everything is manifestly very, very classical. Whatever we see from our birth, if we look around, most of the physics we see around us, unless we make special efforts, special devices, special, very special labs, we see things which are very classical, which means the world is very classical. Now, but we also know the subatomic particles are really very quantum mechanical, but they don't manifest directly. So it's telling you that even if the fundamental constituents of the universe, which are essentially these electrons, protons, neutrons, and the quarks, and all the fundamental particles, if you look at it individually, they're dominantly quantum mechanical. There's nothing classical about them. They require a quantum field theory description. On the other hand, you look at the world around you, the way you see it is completely classical. Now, something must have happened on the way as you took these constituents and put them together to generate this huge amount of matter which we are made of. to make them look classical. So though the fundamental starting point of particles are quantum mechanical, once you put a lot of them together, everything starts looking classical. So some of the quantum information, if you wish, is kind of being not there manifestly, it's kind of lost. Otherwise, one would imagine that the world should be dominantly quantum mechanical, because you think that, if somebody told you that I have built a thing out of building blocks which are dominantly of certain character, and once you have built the whole thing with lot of those fundamental building blocks, you would expect that the property, very fundamental property of this building block will be manifest on what you have built out of it. Now, here we are with a very strange situation where I know that my starting point was absolutely quantum mechanical. Electrons, protons, neutrons, quarks, whatever fundamental particles you can think of are very, very quantum mechanical, and the matter is made out of it. But once I have made matter out of it in a stable state, this is manifestly very classical. It shows nothing quantum mechanical unless I make very special efforts, which is telling you that the quantum information gets mixed up and manifests itself as a classical kind of theory once it goes to macroscopic scales. So that gives you immediately tells you that it's going to be very challenging to make quantum devices, because once you put a lot of it together in an uncontrolled fashion, you are not going to use quantum mechanics anymore. It will look dominantly classical. You have to make special efforts. So what we want is, of course, we want to build quantum circuits, for example, and macroscopic scales. Of course, it's not good enough that I built exactly one qubit which I want to manipulate. That's not the idea. I want to build a quantum computer, which means I want the number of qubits I need to do this is Avogadro number of qubits. That is when I can make a really large computer which I can make use of, right? So now it's telling you that the way nature works is, even if your starting point is quantum mechanical, each electron is like a qubit. If you think of the electron spin, once you put a lot of them together, there's nothing quantum mechanical about it, unless you put special efforts. So it is very hard to keep the quantum nature of fundamental quantum particles in place and manipulate them in a quantum mechanical way, because the natural tendency is that it will lose it. So that is exactly where the challenge comes from. So I will try to tell you in the next part of the story, if time allows, what I will try to tell you is that there are these ideas of new state of matter, which are called the topological state of matter. Topology is a branch of mathematics rather than physics, but I will tell you how it can help us to build qubits which are protected from this environmental effects, which will make it look classical, right? The main idea is that how do I decouple my qubit and keep the quantum information intact as I do operations with it? That's the main challenge. And to do this, I have to make sure. So if you say that, okay, I'll find a way to completely isolate the qubit. If you have found a complete isolation, that's very bad, because that basically tells you that you cannot manipulate them. But if you cannot manipulate them, you cannot make operations on them. So you want a conditional access to them without destroying the information. And that's exactly the hard part. And topology somehow brings in, topological state of matter brings in some answers in that respect, which tells you that you might be able to do this without disturbing the system, because there are topological protections to these qubits. So that's the second part. I think I will not get into quantum computation there. I'll try to convince you such state of matter exists, and I'll try to give you an example of the simplest state of matter which will do this for you, which will make a qubit which is topologically protected. Okay, so let's start with the first part of the presentation. Can you see my screen? So is this my cursor and my screen visible? Hello? Yeah.
Yes, the screen is visible.
Yeah, okay, fine. Okay, thank you. Yeah. Screen is visible. Yeah. Okay. So yeah, as I said, this will be an introduction to the quantum world and a bit of quantum information first. So if you think of it, I mean, one of the greatest mind who has gotten the Nobel Prize because of discovering quantum effects was really Einstein. Einstein was really into the physics of general relativity and gravity mostly. That was his primary interest, and that is where all his really seminal contributions are. But he also discovered this idea of photoelectric effect, which tells you that there is something quantized about this energy, and there is a threshold which you need before you can kick out an electron from a piece of metal by shining photons, which also told us that the photons have energy in packets. It's not a continuous spectrum, but these photons essentially, so the light the way we understand light from electromagnetic theory, if you look at Maxwell's equation, is really tells you that light should have energy which is continuous. So energy is not quantized, but once you quantize the electromagnetic theory, what you get out of it is photons, and photons really have quantized. These are packets of energy. These are not continuum of energy, right? Energy packets. And the experiment which he proposed was this photoelectric effect, which was observed, and it actually confirmed this fact that light indeed comes. If you look at the fundamental construction of light, it indeed comes as packets. It's not continuum, right? So that gave us a first hint of an experimental hint of the very presence of quantum mechanics for these particles. Of course, we are in this case, we are not talking of electrons or positrons or something like that. We are talking of photons. But the interesting part is that when Einstein started thinking about quantum mechanics as it was proposed, he was very, very unwilling to accept the idea, because I think he kept on saying this: God doesn't play dice with the universe, which is also like saying that God doesn't, if there is a God who built the universe, I don't think he believed in God. I don't think that's the idea. That's not the message you should take out of it. I think what he's trying to say is that the world around us is more deterministic than as it is pretended by quantum mechanics, because quantum mechanics intrinsically is a theory which allows for events which are probabilistic, in a sense not deterministic. And this was not something Einstein was very comfortable with, though he discovered the photoelectric effect was really an initial confirmation of quantum mechanics, and it was proposed by him. But still, he had this firm belief that so I think you can go back and read this. There's something called a hidden variable theory, which these people came up with, which essentially said that probably the deterministic theory is hidden behind, you're not able to see it, and that's why the quantum mechanics is looking so probabilistic. But actually it is not. So that's what Einstein believed, though he was one of the first guys to kind of propose an experiment, confirmatory experiment for quantum mechanics. And later on, we'll see Einstein also came up with this idea of Epr paradox, which I will get into, which essentially addresses one of the most weird things about quantum mechanics, which is, if you naively look at it, it looks like action at a distance, right? A very non-local kind of effect, which comes through what you call the quantum entanglement. So I'll come to that later. So that's really the historical starting point. And then I think this is an idea which is a word by Philip Anderson, who is I would say a father of condensed matter physics, a quantum condensed matter physics, a very insightful person in this subject. And he used to say this mode is different. And this word has a very important implication here, because this is what I was trying to tell you, that of course the fundamental particles are dominantly quantum mechanical, but once you put them together, it's not guaranteed that they are going to behave quantum mechanically anymore. And that's the essence of saying that's one of the essence of saying more is different, because once even the microscopic particle are definitely quantum mechanical, but the macroscopic world, which is built out of the microscopic quantum mechanical particle, collectively can behave very different than the quantum physics itself, which is the classical world. So I always bring in this idea of Anderson, who essentially stressed this point: mode is different. It's like saying that if you might know individual persons, I mean, even it works as a social experiment. If you think of a single person, you might know a single person very well and his behavior. But imagine an angry mob who is into destruction. If you add a person whom you know personally, you would never think will get violent, but as a part of an angry mob who is upset with something, he might behave very, very differently collectively. So collective behavior can be extremely different than an individual behavior, right? And this is something we know even at a social level. Same is true with matter, and particularly when you think of the world around us, this is a classical example where the fundamental world is quantum mechanical, but the emergent world is very classical, and we have to pay special attention to find quantum mechanics in this world. That is why we need specialized labs. Now, what are the surprising elements of quantum mechanics? One of the most surprising, which really surprised the world when prediction came in, is essentially the quantum tunneling effect, which tells you that if you are in the front of a mountain, right? Classical mechanics will tell you that if you have to penetrate through the mountain, that's impossible because there's a large barrier, and the only way you can do it is climb through the mountain. But if you do not have the energy to climb through the mountain, the probability that you will go through the mountain, go up the mountain and go down and cross the mountain is practically zero. Now that is where quantum mechanics tells you, no, this is not true. You have a possibility, even if the barrier has an energy barrier is much larger than the energy of the incident particle, even then the particle has a finite probability to cross the barrier. And this is absolutely what is called the quantum tunneling effect. And this is absolutely beyond classical mechanics. Classical mechanics never allows for such a thing, right? This has very nice applications in terms of, for example, STM and so on. It has nice applications in transistors. It has nice application in all the touch devices which you're used to using these days. So initially, when this proposal was made within quantum mechanics, most people thought this is a violation of energy conservation. But this is indeed not a violation of energy conservation. This phenomena happens conserving energy, and that's the whole point. So that is a picture. This picture depicts that. It's not that you are climbing the hill and going down. That's exactly the classical way of doing things. In quantum mechanics, there is a possibility that you keep the energy what you have, but you tunnel through it. Right, exactly as the essence of a tunnel is, you essentially penetrate through it rather than going over it, right? And that possibility exists within quantum mechanics, which is not there in the classical world. So that's one of the surprise elements of quantum mechanics. As we know that the diodes and the transistors, essentially all the tunneling devices, essentially is based on this physics, and this is very well explored. It got the Nobel Prize. IISERK got the Nobel Prize in 1973, and then I think this technology has caught on, and you of course know that this is a very popular technology which is based on really fundamentally on quantum mechanics and quantum tunneling. Now comes the other aspect of quantum mechanics, which is really the quantization of energy. Now, if you look at an atom, what we would think is that if you think of the classical world, then it is more like saying that so if you think of the stability of an atom, essentially that is where Bohr came in, that if you look at an atom, we know that there is a proton sitting at the center, or there's a nucleus sitting at the center, and then there are electrons going around it. This is the picture we have in mind. But starting from classical mechanics, when you start thinking about this problem, you will say this is absolutely unstable system, because we know if you accelerate, rotation is essentially fundamentally a motion which corresponds to acceleration. And if you accelerate a charged particle, we know from classical mechanics or classical electrodynamics that such a particle will always emit photons. It will essentially emit electromagnetic radiation. So if it emits electromagnetic radiation, it's going to lose energy. And if it is going to lose energy, finally, it will spiral around the nucleus and fall into the nucleus, which is essentially telling you that if this is the construction of your atom, this cannot be a stable construction as far as classical mechanics is concerned. And that is where Bohr came up with this idea that actually you really do not have all possible energies allowed in such a system, and energies are quantized. So it's essentially telling you that you can't, though you have the electron going round and round, this electron is not allowed to take any energy it likes. It has to be in particular energy shell, and in general it's not a continuum, it's a discrete spectrum. That's again a outcome of quantum mechanics. It tells you that if you put a particle in a box or a confinement, in this case the confining potential is essentially the attractive potential of the nucleus, which is keeping the electron bound to it, and in a confinement, when you put a quantum particle, then its energy levels are quantized. It cannot be continuous, right? That's again a surprise from quantum mechanics. And for example, that explains why an atom is stable and it simply doesn't radiate out electromagnetic wave and the electron falls into the nucleus and the whole thing annihilates. That doesn't happen. And that's why matter is stable. So it's fundamentally important as far as the stability of matter is concerned. Otherwise, you can imagine that the whole thing will collapse into a zero-dimensional object. It will not even have a finite dimension. The fact that there are energy levels around the nucleus is telling you that it has a finite volume and it is rigid. You can't really penetrate through it, right? It won't collapse into a single point, which probably a nucleus is of the size of 10 to the power minus 13 or minus 14 meters, right? That's like a point particle, right? It has no dimension. So if you build matter out of it, it will everything will collapse. Right? This stability is very important, and that tells you that matter is stable, and quantum mechanics is at the heart of it. Now, other very interesting technologies which gave us this quantum mechanics allows us to do is essentially these, I don't know if you are aware of this quantum corals. So these are essentially arrangements. So what has been done here is, you see that there's a combination of a copper atom at the center, surrounded by iron atoms. So they are saying that here there are 48 iron atoms, and then there is one copper atom at the center, right? So this image is about 5 nanometers, shows a copper surface, or there's a copper surface where a copper atom are contained within an enclosure quantum of 48 iron atoms, right? So these are, I think, these spikes you see around it is indeed the organization of the iron atom, and then at the center there is a copper atom, and this image has been taken using an STM. So STM is essentially a what is called a scanning tunneling microscope, and the way it works is that it has a very sharp tip where there is actually 1 or 2 orbitals sticking out, and from these orbitals you manage to tunnel electron into the surface, and this tunneling current essentially senses the topography of the surface. So essentially what you can do is, at a very microscopic scale, as you can see here, this is about 5 nanometers, the resolution is about 5 nanometers, where you are able to see things, visualize things in a very precise way using quantum tunneling. So you can imagine that this picture is nothing but the tunneling current. So essentially what one is doing, exactly like you have in transistors tunneling current going through the device through tunneling, here essentially there is a tip, STM tip, and this STM tip is trying to inject electron into the system, and it is sensing where the electron goes easily and where it doesn't go easily. And if you kind of map this ease of electron to go in, which is like the amount of current, into a color map, then what you will see is the profile which is shown here, right? This is a color map of the current, if you wish. So that is very precisely. So essentially, such precise, microscopic tunneling is giving us a resolution of the surface which is unthinkable, right? So quantum mechanics essentially allows you to do this. So that's again an example where quantum mechanics is at work as a tunneling device. Now, quantum sensing also, this is something which is this is a picture from Apple, where they have they have put these quantum sensors, which are again tunneling devices, which makes the screen touch sensitive, right? So again, we see that presently in technology, the quantum tunneling devices are all over the place, and this is something we are using all the time. But this is not the kind of use we are thinking of when you're thinking of quantum computation. This is more or less, I would say, from a quantum computation perspective, this is more or less a reasonably uncontrolled use of quantum mechanics. A controlled use of quantum mechanics would be where you actually monitor each individual electron's wave function and see how the wave function of the individual electron is being deformed, and how information is encoded into it. Here, that's not the idea. At the end of the day, what you're interested in is this very tiny current which you want to sense. So it is not that you are really paying a lot of attention to the quantum information which is there. You're just paying attention to the fact that you can harvest this quantum tunneling effect, where an electron can tunnel through a barrier which is much larger than the energy content of the electron. That is what you are harvesting, but you are not really paying attention to how the electron's wave function is changing as it tunnels through. So you're not interested in quantum information. You are more or less interested in more technological aspect, which has to finally do with this current sensing, right? So though it's a quantum device, this is not a quantum information device, right? We are not interested in the information contained by quantum mechanics. Now, other interesting thing about quantum mechanics, which is absolutely surprising, is of course the wave particle duality. This tells you that when you think of fundamental particles, when you think of an electron which is staying in a nucleus, you cannot really think that electron is a point particle which is going round and round. That's not a correct picture. We know that electrons are living in orbitals which are described by this S wave, P wave, D wave, and so on and so forth. And it tells you there is a distribution. S wave is essentially an orbital in which it is uniformly distributed around the nucleus, right? Which basically means I really don't know where the electron is. I cannot think that at this instant of time electron is here. Electron wave function is all over the place, right? It is spread out in a spherically symmetric way on a shell around the nucleus. So though it is a particle, it has a dual nature in the sense that it also behaves like a wave at the same time. So the particle wave duality, again, I mean, you can ask this question, why is this something which we do not see it macroscopic scale? We do not see it at macroscopic scale because it is related, the wavelength of this of a particle is somehow related to the mass of the particle, and once you become very, very massive, the wavelength becomes very, very tiny, and once the wavelength becomes tiny, what dominates is the classical overlap and not really the wave function overlap, right? So basically, once the wave function is the wavelength extent is very tiny, you really won't see interference effect, because for interference you need wavelengths to match reasonably well and wave functions to overlap reasonably well. So that is why we don't see it for massive objects in macroscopic scale, but at microscopic scale these are very dominant. And essentially it means that particle can interfere with each other, right? So particle has a dual nature. That's another complete surprise of quantum mechanics which classical world doesn't have. And this has many applications, so I will not get into that. So now one of the, so now moving towards technology is one of these examples. This is one of the classic experiment which I'm showing you here. This picture is taken from this experiment which was reported in the Weizmann group in Israel. So what they did is they built a quantum device which is exactly like a two-path interferometer. It's like a Young's double slit experiment which you are used to thinking about in the optics. So essentially you have two slits and you have an incident wave, incident electromagnetic wave or light wave which is coherent, and as it passes through the two slits, it finally gives you an interference pattern on the screen. So the question would be that can I do such an experiment with an electron? And that's a very hard experiment. If you of course think of electrons in vacuum, this is a reasonably easier experiment because you are doing this in vacuum, and that's very much doable, and this was done in the past. But this is not what we are interested in. If we say that I want to use quantum mechanics at a device level, we have to achieve this with a solid state setting. Solid state setting means an electron which is inside a lattice. Now, once you start thinking of an electron inside a lattice, that becomes a very complicated story, because inside a lattice you have phonons, you have all kinds of impurities, and cleaning the system up is very hard. So it is not like an electron in a vacuum. So if you are not in vacuum, if you are inside matter, performing such an experiment is extremely difficult, as I said before, because isolating an electron is very difficult, because it's almost inevitable that electron will, before it could interfere with itself, it will start scattering with other scattering centers and lose its phase information. If it loses its phase information, then of course you cannot have interference, because interference is completely based on phase information, right? So here, what is being shown here, I'm kind of zooming in. What is being shown here is that this is a device which is exactly using the same technology as it used in ICs. You have ICs where you have two-dimensional electron gas. This is exactly a two-dimensional electron gas, on top of which you see these protruded things. These are essentially some kind of the bridge here, the gates here. You see that there are many gates here. So beneath you have a two-dimensional electron gas which is produced in an IC. On top of it, what you do is you put metallic gates here. Metallic gates have been put here to confine the electron in a trap. And in between, you put a puncture by putting an large electrostatic potential there using this bridge gate. And what you do is, from the source electrode, you inject electrons and you let it go through this path, and you let it go through this path. And then you measure the current here and look at the pattern of the current as a function of the energy of the incident electron. And what you expect to see is oscillations which is proportional to the path difference or the phase difference the electron will accumulate over one circular motion about this device, right? That's what you expect to see. So essentially what you're saying is that once you shoot an electron, it should behave like a wave, and it should self-interfere and give you an interference pattern which is being detected as a current. Now, if you see coherent oscillation in current as a function of incident energy of the electron, which you could hopefully, kind of control in an experiment, then essentially you will say that I have seen electron interfering with itself, even in a device which is a solid state device, and then you can hope that you can harvest these things for making some quantum devices, or use it for quantum information processing and quantum computation and so on. But I think before you get there, I think the main question these people were asking is, so why is it that we don't see quantum mechanics at macroscopic scale? Because it gets hindered by external agents which comes and collapses the quantum state, and it loses phase information. Sometimes you altogether lose the state, right? That is why you don't see. So here the controlled experiment they did is they called it which path interferometer. What does it mean? It means that, so the main point of quantum mechanics was that when you shoot an electron and you're trying to see an interference pattern here, what you must not ask is that which path did the electron take. If you try to measure which path did the electron take, quantum measurement theory tells you that the state will be collapsed into that particular slit. So imagine that there are two slits, and electron is passing through the first slit, electron is passing through the second slit, but because it's a wave, electron is not just a particle, it's also a wave. It can simultaneously pass through the first slit, the second slit. It doesn't have to wait, right? It's not like that it can only go through the first or the second. An electron, being in dual nature, is also a wave, and being a wave, it can simultaneously pass through the second and the first slit. That's the most important point, and that is where quantum mechanics comes in. Now, where does quantum measurements comes in? The measurement comes in the following question. Now, if you ask this question that I want to know, as the electron is impingent on this interferometer, do I want to know that if the electron took the first slit or the second slit? The moment you do this, you essentially measure the electron and collapse the electronic state into a position eigenstate, and it will collapse into one of the slits. And if it collapses into one of the slits, then interference pattern is gone, right? So that's very important. So you cannot disturb the electron as it is behaving like a wave. So it's telling you that if you want to take advantage of the fact that electron is behaving like a wave, you cannot do a measurement or a disturbance in between, because if you do that, its particle nature will become dominant. It will collapse into a single particle state, and it will just get localized at a single point. So they performed a controlled experiment to verify this theory. So what they did is they put some electron sensors. These are this, you see this QPC here, this small QPC, this plunger voltage here. Can you see my cursor? So just, okay, let me zoom it out. Can you see my cursor here? Can anyone say yes or no?
Yes, sir. Yes.
Okay. So the point is that you see, you inject electron from here, the electron can go in this path, the electron can go in this path, and you see an interference pattern here. What they have done, across one of these arms, they have put a device here where they can inject electron and collect electron there. So it is like what is called a quantum point contact, and you are continuously allowing electron from a side flow. You can think of a side flow, and what they can do is, at the receiving end, they can look at the statistics or the fluctuation of the current which is passing through this device. So the idea is that once the electron is really passing from here, if another electron is passing from here, they will feel each other, and they will kind of collapse each other's state, and that information will be collected here. So essentially, every time an electron passes through this arm, you will see a small blip or a peak in the current or a dip in the current, which is collected at the QPC. So the idea is, when you will not measure this current and not detect this current, you should see a perfect interference pattern here, because you are not asking this question. I'm not trying to measure which way the electron went. Okay, that's very good. Now you switch on this QPC and start measuring the current here, which is kind of detecting which way the electron is going. And every time the electron takes this path, you actually have an idea it took this path, which means you are measuring really the fact that the electron went this way. The moment you switch on this device, what you expect is that the interference pattern here should lose its visibility and get worse and worse as this measurement gets better and better. And that's exactly what they saw. That is why they call this experiment a which path experiment. So it really confirms this idea of quantum mechanics and particle wave duality, that as long as you don't really try to measure which way the electron went, everything goes fine. You see an interference of electron, but the moment you try to measure it, it collapses, and it starts behaving more like a particle than like a wave. Okay, this is a beautiful experiment. You can look this up. This was and this is another experiment which is a more recent experiment, published in Science. You can send me emails, and I can give you more references on this. But I think this is a beautiful field, and the device development has gone a long way since this experiment has happened, and we are doing much smarter experiment these days on quantum chips, on this two-dimensional electron gas, and we are hoping that this will bring in really quantum technologies, right? It will take it forward. So that's particle wave duality and its most recent experiment. So let's now move on to, I think, okay, so yeah, so I can now the uncertainty principle. Of course, at the heart of it, all at the heart of it, one of the most important concept is the uncertainty principle. It's telling you, so again, uncertainty principle is again a statement of the probabilistic nature of quantum mechanics. So here is a very nice cartoon, which is really, so it's giving you the map of the building. So it's called the Heisenberg Department of Physics. And then if you have a map which is quantum mechanics based, it will only tell you probably you are here with probability this much, right? 50% probability, probably you are in front of my office. This is, I think I really like this cartoon. Anyway, so the main idea is that what it's saying is that quantum mechanics is intrinsically probabilistic. What it tells you is that the information in general which you are interested in quantum mechanics is not really the expectation value. So you know that there is this what you call the expectation value. Expectation values are really averages of some quantity, but expectation values are good quantities to look at when there are no fluctuations. Imagine that I'm measuring current and I ask you how much current are you measuring. You're doing an experiment and you're measuring current, and somebody asks you how much current are you measuring. Somebody tells you it's 5 ampere. Now imagine a situation where though your average current is 5 ampere, if you look at the fluctuation of your data you're collecting, it is, let's say, 10 ampere. So the current actually is fluctuating between 5 plus 10 and 5 minus 10. So if you are measuring an average of 5 and your fluctuation is of the order of 10, then this measurement, if you give me this information that I have an average current of 5 amperes, this is an absolutely meaningless statement, because it's not giving me any information about that system, right? Because it's a meaningless, right? This fluctuation is much larger than the average. So averages actually are meaningful to quote to quantify a physical phenomena when the fluctuations are small or maybe they are zero. So in quantum mechanics, we of course put a lot of stress on expectation values, which are average of some physical quantity, some Hermitian operator. In this case, in this context, when we most popularly it is referred to as the position and the momentum operator. But the point one is trying to make is that when you're looking at the average of a quantity, that's not giving you enough information. What you must look at is the standard deviation of your data rather than the average. For example, if you have a free particle, think of a free particle. So imagine you are in one dimension and you have prepared a free particle wave, right? So prepare a particle which is free and you leave it in one dimension, which is extended from minus infinity to plus infinity. Now, if somebody asks you this question, that what is the position of the particle, what is the answer you will give? What you will do is, of course, if you have to give an answer, you have to make a measurement. That's the right way of doing things, because if there's a question, the only way we can answer it is by doing an experiment. So you will go ahead and do an experiment. Now when you say you will try to find its position, essentially it means you have a position operator, right? And when you use the operator on this quantum state, my fourth postulate of quantum mechanics tells me, which is the measurement postulate, it tells me you're going to collapse the state into one of the position eigenstate, right? That's what it tells me. So every time I make a measurement of the position of the particle, is going to collapse the particle into one of the position eigenstate, which basically means every time you measure it, you will find it at, say, maybe sitting at 0, maybe sitting at 0.5, or maybe sitting at x equals to 5, x equals 25. And that information, as you can imagine, that if it is over from minus infinity to, if the full space is minus infinity to plus infinity, it has a perfect parity symmetry about x equals to 0. So if you look at the average, you will find every position with appearing with equal probability if you do a large number of measurements. Let's say you do a really huge number of measurements so that you have enough statistics, and you took data and you just took the sum of the data, it's going to give you 0, because you're going to find the particle with equal probability to its left and to its right. That's what the measurement is going to give you, which basically tells you that this is no information. It's not giving you any information. Then you can ask this question, what is the standard deviation of my data, right? Which is the uncertainty. And that's an important information. So if you measure, so essentially what one is saying is that if you measure the position of the particle and if you measure the momentum of the particle, you will get a data set. Now, looking at this data set, you can essentially calculate different moments of this data. So the first moment, or the most trivial thing which you can measure, is of course the average value, which is what we'll do, which is the expectation value. Now you can calculate the expectation value of momentum, you'll calculate the expectation value of position. The position will give you 0. The momentum, if you prepare the particle in a free particle eigenstate, of course it's a momentum eigenstate, you will get a definitive momentum, which is more like classical physics. Now, what is important? That's not important. What is important is how much is the fluctuation. What you realize is that if you just stayed happy with the fact that the data's average is 0, then your conclusion would be the particle is sitting at 0. When I prepared it in a free eigenstate, free particle eigenstate, your conclusion would be the particle is sitting at 0. Of course, you know that this is a completely wrong conclusion. This is not a correct conclusion, which means the average is telling you nothing. When you look at the standard deviation, if it is a free particle, you know the standard deviation will tell you that your fluctuation is infinite. It's totally spread all over the space. This fluctuation can be as large as it wants. It's totally fully spread. And that is where we'll get an idea that the particle is not sitting at 0. It is spread all over the place. You really cannot tell where it is because it's everywhere. On the other hand, when you measure a momentum, it's giving you, because it's a momentum eigenstate, it's giving you more like a classical information, because that is what we say in classical mechanics. When you make a measurement, there is no uncertainty. It is very deterministic. The particle is sitting here, I'm making a measurement, I will tell you precisely the particle is at x equals to 5 or 0.5 or whatever, and you will always find it sitting there no matter how many measurements you make. Only in quantum mechanics we get this strange thing, as we are getting now, that the particle is everywhere. So that's a very strange feeling, right? You can't say the particle is everywhere in classical mechanics. We never make this statement. But if simple free particle wave function is saying the particle is omnipresent, it's everywhere. On the other hand, if you look at the momentum, that has, because the eigenstates have a deterministic number associated with them, that's more like a classical thing. When you measure it, every time you measure it, you're going to get the same number. So if looking at the momentum measurement, you will feel it's a very classical system because you are getting a deterministic number with 0 spread. So the standard deviation of momentum will be totally 0 in its momentum eigenstate. But if you look at the positions of that particle, it's totally spread, and that will give you an idea something very quantum mechanical is going on. Right? It's infinitely spread. So that is the essence of uncertainty principle, is telling you that the physical description of quantum mechanical system is intrinsically probabilistic. It is not deterministic. And that exactly goes back to what Einstein was saying, that God doesn't play dice with you. That he was very uncomfortable with the fact that you will write a theory which is intrinsically not deterministic. It is intrinsically probabilistic. He was extremely uncomfortable with this idea. Okay, so that's Heisenberg uncertainty principle, and let's move ahead. Now, really the one of the most strange things about quantum mechanics, which is essentially this, which is this idea of entanglement. So the idea of entanglement goes back to this idea, the very postulates of quantum mechanics. So let's say, what are the postulates of quantum mechanics? That the postulate says that in classical mechanics, when you describe a state in classical mechanics, that essentially in general, if it is a collection of particles, then you will say that a state in classical mechanics is a point in the phase space. Right? If you have a phase space, which is like the x-axis, let's say, is position, the y-axis is momentum, then a point in the phase space is essentially what tells you what is the state of the particle. If somebody asks you at tth instant of time, what is the state of this particle, your answer would be, it is this point in the phase space. Right? That's what we know. But now, once you come to quantum mechanics, this is an invalid description, simply because you cannot, when an uncertainty principle comes in and tells you that you really don't know the position and momentum simultaneously. They are not commuting observables, right? That's not a description. You can't use that description. So what it tells you is that the description of the system is essentially something which is very abstract. You have to determine the Hilbert space of the problem, and the description of the state is essentially in terms of some vector, abstract vector in the Hilbert space. Right? That's the description. It's very different than this classical starting point, which was very physical. This is very mathematical, very abstract. That the starting point is this, that you say is physical state of a system is describable by a vector in the Hilbert space. Now, if if you have multiple parties, so of course if this is description is only restricted to a single particle, then it's not a problem. You in the rest of the quantum tunneling and all these effects are in place, but you don't get this weird physics of what you call entanglement. The complicated question comes in. The weirdness of quantum mechanics really manifests itself once you promote yourself to describing multiple particles at the same time. That is when the complication comes in. And let's say that you are trying to describe, again, of course, this description always remains that finally the state of the system will be described by a vector in the Hilbert space, and the time evolution of this vector in the Hilbert space, which is the state of the system, will be given by Schrödinger equation, for example, right? So this is how I know how to evolve the vector in the Hilbert space, right, as a function of time. Now the question would be that if you have two particles and then you have such a vector in the Hilbert space and you are evolving this in time using the Schrödinger equation, does something very weird happens? And when I say weird, anything weird happens, this has to be connected with the fourth postulate of, I mean, when I told you the first two things, that a state is a vector in the Hilbert space in quantum mechanics, and the fact that Schrödinger equation is the equation which gives you dynamics, which basically tells you how the states evolved in this vector space, are the first two postulates of quantum mechanics. The fourth postulate is essentially about the quantum measurement, that when you perform a measurement corresponding to some physical operator, the state collapses with a certain probability into one of the eigenstates of the measurement operator, right? So what you have to put together is the fact that that a state of two particles is essentially some kind of vector in the Hilbert space and the measurement postulate. These two put together, you will see, will create a lot of confusion, which we cannot conceive as far as the classical world is concerned. So there are certain wave functions which you can write for two particles, which we call the product wave function, which is more like saying that if the first particle is described by a wave function psi1 and the second particle is described by a wave function psi2, then the description of the state is psi1 direct product psi2 or psi1 times psi2. This is the most simplest wave function you can write, and this has a description which is reasonably simple and doesn't create any confusion. But if you write anything which is different than this prescription, where the total wave function for the particle cannot be written as a direct product of the wave function corresponding to the first and corresponding to the second, then you can show that once you perform quantum measurements on the first and the second particle, the outcome of the quantum measurement cannot be conceived within the classical notions, right? It will have surprises, and that's exactly the point of entanglement. I think so just how much time did I? Yeah, so it's 40. So should we take a break here and take questions? Maybe I've come in quite some way now. Are there any questions? No questions.
Yeah, you can continue. I think at the last they will ask some questions if they want.
Okay, fine. Fine. Okay. So so as I said that.
Sir,
Yes.
just
Yes,
one
please.
question, sir.
Yeah,
Sir,
please.
if we talk about the experiment which you have shown just here, means where the
Right.
electrons
Let me go
are
back.
fired.
Yes, here.
Yeah. So
Yeah.
if this one is means here, if the electrons, which is means the main thing is that when we are firing, we do not actually know that which path the electrons are going. So that is the main concept for
Absolutely.
which we can see this.
Yeah.
So
Absolutely. Yeah.
the
Absolutely.
moment
Yes.
we do this experiment, so
Yes.
does that means through the slit, does that effect remains on the slits? Means,
Very interesting question. I think I understand what you're saying. So what you're saying is that because we are not in vacuum, yeah, this is a very important question. So after all, if the electron is passing through that bridge or this separation, so it is, no matter what, it is given that it's interacting with it. Now, if it is interacting with it, what you're asking is there a back action? right? I
Yes,
mean,
sir. Yes, sir. Yes, sir. Actually, that is the
yeah.
thing which I was trying to say.
Yes, I think the answer to that would be, this is exactly when you want to devise this thing, that is exactly the difficulty. You see, if there's a very large back action, it will also mean that the electron will be dephased and it will lose phase information. So what you have to do is you have to make sure that when you're putting these gates and so on, over the time scale over which the electron is shooting through this device, there is not enough back action to destroy your interference. And it's mostly acting like a potential rather than a dynamical object. We can absorb information or give information, right? See, you are measuring interference which is happening across this device, right? So there is a time of flight for the electron over this device. What you have to make sure is that the interaction time between the gate and this thing, which will have quantum mechanical implications, is way much longer than the interference time. If that is ensured, you know that those back actions are not going to disturb your interference pattern. Does that answer your question?
Yeah. Yeah. Okay. Fine, sir. Though it is, I hadn't exactly understood the concept, what you said just now.
No, essentially what I'm
Can you
saying
please
is,
elaborate it a little bit once
yeah,
again?
absolutely, I will. In a sense, what you want is everything that has been, other than the electron, everything that has been put here should act like a potential rather than something which can really. So if it becomes a dynamical object, it can dynamically take information out of the electron or give information into the electron, right? Which is like saying that it will randomly tamper with the phase of the electron. But a potential won't do that. A potential is static. So essentially what I'm trying to say is that all the devices which has been put around it has to be such that they act like potentials, static potentials, and do not have any dynamical implications. As long as this is ensured, your interference pattern will not get disturbed by all the gates and all the devices which are put around it.
Okay. Okay.
Right?
Understood. Yeah.
So what one is claiming is that over the time scale over which the electron flies through the device, you have designed your system in such a way that it is not interfering dynamically with the phase of the electron. That is being ensured. So that is when, that is exactly the challenge. Now you have to ask this question: how small size should I go to before I start seeing this? That's exactly the problem. This is why in the macroscopic world, though we know that the underlying thing is quantum mechanical, we don't see quantum mechanics because it's washed out. So this device is few microns. It is much thinner than our hair. What you see here is a design which is done. So you can see here. Do you see the scale? So I think that will give you an idea. This is 200 nanometers. This distance.
Yes, sir.
So this will be like 1,000 nanometers. It's
Yes,
like
sir.
1 micron kind of distance. So the whole device is just a micron, which is much thinner than our hair, right?
So how these devices are made, sir?
So they are what they call lithographically patterned. So they have these guns with which they kind of decorate it. They really deposit it, and so okay. So that's an interesting technology. What you do is you take semiconductors, for example. First of all, you have to ask this question: how do I make a two-dimensional electron gas? And that is exactly the IC technology. The whole IC technology is nothing but a two-dimensional a design of a two-dimensional electron gas, which is like saying that you take a p-type semiconductor, a wafer which is a two-dimensional wafer, mostly a parallelepiped of the form a shape parallelepiped, and you take a p-type wafer and you take a normal wafer which is not of any type, a semiconductor, and then you make a junction between them, and then when the electrons from p-type try to seep into the semiconductors in the transverse direction, they get trapped on their own potential, in the sense that every p-type or n-type semiconductor, they will have after all they are stuck to some atomic nucleus, right? And once the electron, so how should I say? Maybe I rephrase myself. What is the best? I don't have a picture here. Do I have? Let me see. I don't really have a picture. Okay, so the idea is that you start from some semiconductor which is, let's say, p-type, and which is designed in a form of a parallelepiped, which is like the IC, and then on top of it you put a normal semiconductor. So because the bottom one is p-type or n-type, it has excess of positive or negative charges, and because of diffusion, it would like to go through this interface, which is, the interface is two-dimensional, as you can imagine. It will try to seep through the interface and go towards the low density region. But as it tries to do that, it leaves behind positively charged nucleus. So that acts like a quantum potential, confining potential, and in the z direction, what you get is a quantum well. And in this quantum well, what you trap is a two-dimensional electron gas. So essentially, what is beneath this device? So what is being shown here, beneath this device, you have a two-dimensional electron gas. And what you do on top of the device is essentially make this deposition of metallic objects. It can be gold. Maybe this is not gold. This is probably, I don't know what exactly is being used, but you put metals and you kind of decorate the metal in such a way that once you put negative voltages on this piece of metal, it kind of depletes the electron from undesired region and keeps the electron confined in the desired region. So you see the point? So inside the semiconductor, somewhere deep inside, you have a two-dimensional electron gas. On top of the device, you pattern these electrodes, and then you put negative potential on it, which depletes the electron from the unwanted region and kind of gives a shape which you desire to get, which is the interferometer in this case. And then you kind of, contact it from the side, inject electrons, and perform experiments. So this is how it is done. Did it make sense?
Yes, sir. Thank you, sir.
Okay. Okay, so we were, I think we were in the Epr paradox. Yeah. So I think this, so what I was trying to tell you is that if you write this if you consider all possible wave functions which are allowed by quantum mechanics, which are not product wave function, they have very strange surprises for the outcomes of a measurement which you can make on such wave functions. And this is something Einstein noticed very carefully, and he was very uncomfortable with it. So that's why I think it's called the paradox, the EPR paradox, Einstein-Podolsky-Rosen paradox. And they came up with essentially an idea which will give you a sense of how weird this object is. So of course, when you see something weird, you have to you can't just say that it is weird. You have to also say that can I quantify the weirdness or the strangeness of this object, of this wave function. So essentially, they provided a quantification of the strangeness of these wave functions. And particularly, it felt like that what you have is non-locality, which is not true. So this is how many people conceived it, but that is indeed absolutely wrong. So Einstein's the special theory of relativity tells you that you cannot have. So imagine that there are two distinct, nodes, and you are trying to send signal from the first node to the second node. Then the statement is, if you're really trying to send a physical signal, no matter what you use, what medium you use, what device you use to send a signal from A to B, the signal cannot be sent faster than the velocity of light. This is a sacred statement. It not only is valid for classical mechanics, like classical mechanics, the classical theory, where theory of light, like Maxwell's equation, of course, are invariant under Lorentz transformations. So it is valid there. Definitely, it tells you that velocity of light is limited to c. This goes all the way into quantum mechanics also, right? So quantum mechanics. So essentially, that is how we get into quantum field theory. When you try to marry quantum mechanics with special relativity, what you get is all these Klein paradoxes and so on, which tells you that there's something special going on when you get into the subject of quantum field theory. So it is a valid statement no matter what theory you are doing. We believe that no matter what you do, you cannot send signals at a speed which is faster than velocity of light. Now, why is that question coming in here? The question is coming in here because let's take an example. So example is, let's say, of two entities. Let's say there is an upspin and there is a downspin, and these are the two objects which we are interested in, and we write a wave function which is of a strange type, which is something which is written below. You see, what one is asking is that, can you write a state which is of the following type? So if I give you two spins, and if they're classical, if I ask you that what is the first spin doing, is it up or down? Or if I reduce the up and down to a yes and no answer, is it yes or is it no? It's a binary answer. It's a classical answer. You will go take the first spin, make a measurement on it. You know that you are going to get a deterministic answer because you have classical mechanics in mind, and then you will say it is either up or down. Now you go to the second guy, you ask the same question, and which means that you make a measurement, and the measurement outcome, what you expect is to be some classical object which is either yes or no or up and down. Now the question would be that can I write a state which is like yes no plus no yes, right? So yes for the first, no for the second, and no for the first, yes for the second, which is like saying that up down plus down up. Now you see, this is a very confusing situation because it's telling you that if I really ask somebody, once you manage to prepare the system in this state, and this state, I think I need to stress something here about quantum mechanics, which is very fundamental to any, this any quantum operations, quantum computation, and anything which you see is quantum mechanics is linear, right? Linear superposition is a fundamental principle of quantum mechanics. Because if I give you a state A and I give you a state B in the same Hilbert space, then A plus B, A minus B, alpha times A plus beta times B, where alpha and beta are two complex numbers, is absolutely a valid state. So that is what it is said, that this is a vector space defined over the field of complex numbers. So any complex coefficient is welcome, right? So any linear superposition becomes immediately a valid state. So of course, these are like what I call the product state, yes and no. So it's telling you that this is describing a state where the first spin is yes and second spin is no. Or the second state is also a product state where it's a deterministic answer. If you make a measurement on the first guy, you're going to get an answer no, the second guy is yes. These are deterministic. But what I know in quantum mechanics is that if I write to a state, I also know the linear superposition of these two states is a valid state of the system. There is no problem. Quantum mechanics allows for start, and that's exactly the starting point of, if you want to call it trouble, you call it trouble, or the beauty of quantum mechanics. This is where it gets beautiful and also confusing at the same time. So it's telling you that it's a linear superposition of two states such that I can neither say the first state is up, neither can I say the second state is down. So essentially, it's a very confused state where I cannot say anything deterministic of the first and the second spin. They are something, but they are not something deterministic. It depends on what measurements you make. Now, what does that mean? That means that imagine that I have prepared the system in this state, and I go to the second spin and I make a measurement. Imagine that I have prepared the system, this binary here. I prepared the system in the state below, and I'm going to make a measurement on the second guy. So imagine that I made that measurement. Once I've prepared the state, I made that measurement, and I found that my answer is no, or let's say the answer is no, which means the state is down. So if the second state is down, which basically means that this operation of measurement will essentially tell me that now if you go to the first state, you will always find the first state in the yes state, right? Because I have already found the first answer to the second guy to be no, right? So it's telling you that the outcome of a measurement on the second guy depends on the outcome of the measurement on the first guy. So there is a very strong correlation between the outcome of the first guy and the second. They are biased in some sense. So once you measure, see, before you made a measurement, the state doesn't tell you anything in the sense that doesn't tell you the first guy is yes or second guy is no, nothing. You can't really say that. It is some linear superposition. When do you have a deterministic answer? You have a deterministic, but the interesting point is you do have a deterministic answer, but when do you get that? Once you made the first measurement, which was uncertain, which was like had a probability to be yes and no both, but once you know that I made a measurement and I have already gotten one particular answer, then I also know deterministically what your answer would be if you do a measurement on the second state. Right? That's a very strange thing to happen, right? But you have both possibilities. It's not that the first state is always yes, so that the second state is always no. So depending on, see, the first measurement is fully probabilistic because you don't know what's going to come out. But once it has come out, you know deterministically what the second state is going to go. So now you think of an experiment where in a lab, in a small lab somewhere in India, I prepare this two spins in an entangled state, and then very carefully, without really letting the state interact with the environment, which is like saying not letting them decohere, I take these states to two parts, absolutely two ends of the world, one in the US, one in India, extremely far away. Now you must pay attention here that this process by which I am kind of first of all preparing the state, that's the process of course which I have to find out experimentally how to do this. But once I have prepared it, the process in which I am physically transporting the state, this transportation really happened in consistency with special relativity. I never ran the state and separated them faster than velocity of light. I will just put it in a truck which has an appropriate device which makes sure that this entanglement doesn't go away, and I will put it there and put it carefully in the US somewhere. Right? That is what I'm going to do, and this process will happen completely in consistency with special relativity. Now the statement is, once you have prepared the wave function and made it completely non-local, and once you're there, then if I make a measurement in India and I make a measurement on the second qubit and I get an answer, then if I do not I do not give this information to my US partner, but ask him to just do a measurement, if he makes a measurement, then I already know what his outcome was going to be, right? Once I know my outcome, and that I know instantly before the measurement has happened, right? That might give you a sense that as if the information has instantly gone as you have done the measurement. This, in fact, that you have done the measurement has propagated to the US. But that will be a wrong way of looking at it, because the information has already gone propagating to the US when you prepared the state and slowly, kind of without disturbing it, actually took it all the way to US. What you did in the process is extended the wave function's physical extent from India, localized in India, to localized between US and India. That you established. The state is already established. It is there. Now, this is a property of the state, that the moment the state is now, you should keep this in mind, the state is already non-local. The quantum state is non-local. It's all over the place. Now the statement is, the peculiarity of the state is that if you make a measurement here and you know the outcome, you instantly know the outcome on the other side. You don't have to make another measurement there. You know it beforehand. There's nothing probabilistic about it anymore. And that's entanglement, and that is not like saying that the information is running from India to US. No, it's not running. It's instantly there because the wave function is already infinitely extended. So there's nothing running here. And so that is the consistency between the quantum entanglement and the concept of non-locality. They are not in conflict with each other. They're completely consistent with each other. And that is where I think Einstein, to clarify this point, I mean, of course, this was not something he again wanted to digest, and he was kind of struggling with it, and then he devised this paradox, which gives you a very solid hint of the fact that something very strange is going on, which are these quantum correlations, which are beyond classical ideas. They're not consistent with classical ideas, so you cannot really use classical intuition to think about them. You have to think differently. It's a very property of the state itself which does this. And I will not get into Bayes' inequality, but that's a very interesting topic. You should look at it, how Einstein kind of logically constructed this paradox. And then from that paradox, essentially, Bayes went ahead and prepared the state, which are called the Bayes state, which actually maximally violate the inequality which Einstein devised. Okay, so that's quantum entanglement, and it can be used as a resource, because I think now you can imagine that between US and India, I'm able to kind of transfer information in a very non-local fashion. So you could imagine that that's exactly so that is where this quantum teleportation comes in. This very idea that you can send something very non-locally and instantaneously from one place to the other. It's not really, again, it's not a violation of causality. It is only saying that you have already established a very, very non-local state. So I think when you think about it, you almost think of this. There was this serial called Star Trek. When I was a kid, I used to see Star Trek with a lot of interest, which had this idea. You could teleport people from a spaceship to a planet and back and so on instantly. And that looked very interesting. But the idea is that if you think of yourself as a full embodiment of a quantum state. So if you think of my full body is nothing but, it's a very complex, but after all, it's just a quantum state. which is in a particular, which is organized in a particular way, then it's only a question of sending the state off far away, which basically means if I am a quantum state as an entity, and there is another quantum state which I build, let's say somebody, maybe my wife, and then we have to perform an experiment to entangle the two in an appropriate quantum fashion, and then kind of send her or myself somewhere else, and then one can do quantum teleportation between the two, something like that, right? So that is the idea. I mean, it's not, as you can see, it's not a simple thing. Essentially what you have to do is first take two entities and entangle them properly. And the biggest challenge is once you've entangled, that's not the end of the story. You can always entangle in a very specialized local lab. To carry it very, very far away and then keep entanglement intact is the biggest challenge. And that is what one is talking about. And that is exactly what is being so difficult. That once you have created an entangled pair, if you want to do teleportation, you have to send the part of the pair off to a very far away world between which you can do this instantaneous, kind of communication. But to do this, well, it's not a communication, because when you say communication, it means you are sending something off and you're receiving something. It's like you have already sent off what you wanted to send off. After that, everything is deterministic. If the game is in a kind of between you and them, you already know what the game is. At some instant of time, you will make certain measurements, you will have the outputs, and you will already know beforehand what they're going to measure, because the state there has already collapsed into the desired state or the undesired state, depending on what outcome you have here. So that is the story of quantum teleportation and quantum entanglement. So now, of course, so we know that the classical ones, just to wrap up, we know the classical computers work on binary logic, and that is exactly where we want to bring in, quantum mechanics, because we want to bring in new possibilities, and to see how new possibilities comes in, even at a fundamental level. You see that here the binary logic works on just two numbers, zeros and ones, which you can say are two states. And in quantum mechanics, as I said, linear superposition is a fundamental principle. But it is not just linear superposition. I think we have to pay attention to the fact that it is linear superposition defined over the space of complex numbers, not real numbers. Because if you say that I have two states, psi1 and psi2, and I'm only allowed to include real numbers in its coefficient, which means I have alpha times an up state plus beta times a down state, and this is a valid state such that mod alpha squared plus mod beta squared is 1. That is normalization. Of course, every state has to be normalized, because then probability will behave in a proper way. Now, alpha times state up plus beta times state down is a valid state of quantum mechanics. And if you say it's only real numbers which I allow, then of course you see that alpha square plus beta square is 1 is just a circle. So what you did, you initially had as binary numbers, you just had two possibilities with two states. The first possibility being up and the second possibility being down. The first possibility being 0, second being 1. Now, if you say I'm going to define a vector space over the field of real numbers, then you expanded the possibility to a circle, which is a huge expansion. So coming from 2 points, which is 0 and 1, you extended it to a continuum of points. The states are on continuum. With 2 states, you have a continuum of points, which is circle. But the point is that's not what we are. We have even more, because we are defined over the field of complex numbers, where alpha and beta are complex numbers, and mod alpha square plus mod beta square is 1. If you think about it carefully, you will realize alpha is a complex number, so I can write it as z1 plus iz2. Immediately, also beta is a complex number, which means I can write it as z3 plus iz4. And now if you plug it in, mod alpha square plus mod beta square is 1 becomes an equation which looks like, I'm not showing the slides, I'm just saying, please don't get confused, which is equivalent to saying z1 square plus z2 square plus z3 square plus z4 square is 1. Now see, this is an equation of a circle in 4 dimensions, right? That's what it is. So it is called a 3-sphere. So essentially the space of states suddenly, because it is defined over the field of complex numbers, it has suddenly become a sphere in 4 dimensions. It's really huge. And that is what makes quantum mechanics very beautiful and very useful. See, the principle of linear superposition already gave you this expansion, that what was 0 and 1, now the space of states, just with 2 independent states, 2 orthogonal states, has become a 4-dimensional sphere, right? And that's the essence of the story. You can imagine that at least even if you think of a resource, suddenly your resource has exploded, right? So I think to show you a very nice article on this, so I kind of show this in many talks, that somebody calculated what is the limit, what is the smartest computer you can build, and what is the maximum number of logic operation it can do in 1 unit of time. And this is a paper which actually tries to estimate that what is the fundamental limit on quantum computation. How fast, if you allow for matter to be super smart. Super smart means, when you say something is super smart, of course you have to go back to fundamentals. Fundamentals means fundamental physics. The fundamental physics has some fundamental constants. What are the fundamental constant? H cut is a fundamental constant. Velocity of light is fundamental constant. The gravitational constant is a fundamental constant. So what this Seth Lloyd did is he made an argument saying that if you have 1 kilo of matter, which is the smartest possible, let's say, state of matter, what is the fastest computation you can do with it, and what is the absolute quantum limit on it? And he found a limit on it which is expressible in terms of the fundamental constants of nature. I think it's a very interesting and encouraging paper. I would encourage you to look at it if you are interested. It really sets the bound on what we can do with a quantum computer. What is the extreme limit given the nature of quantum physics we have in? And even gravitational constant comes in, and that's very, it's very intriguing. I think with that I would like to stop, because I did not hear any questions. So I was thinking of getting in the topological state of matter, but maybe I take some questions on this section, and then if time is there, I give you a bit of hint of this topological state of matter and how it can be used in quantum computation. Yeah, thank you.
Yes, thank you very much, Professor Sorin Das.
Thanks.
Mr. Pritham wants to ask some question, I think.
Oh, please go ahead. Please go ahead.
Pritham is here. Yes, Mr. Pritham is here. Sir, he has a question that what are the basis to consider the particle as a wave-like behavior or particle behavior? Is there any specific conditions?
Specific conditions, I see. Yes, it is. It goes back. Okay, so I think one way to answer this would be really this de Broglie wavelength. This is the genius of, so here you see that the wavelength. So what is one saying? That particle can behave like wave. Now, when you say something is a wave, what comes to your mind is essentially a fundamental thing, which is wavelength, right? You have to say, what is the wavelength of my wave? For example, when you think of a diffraction experiment tells you that light is a wave. Now, when is it that you see a dominant diffraction pattern? You see a dominant diffraction pattern when the slit width is matching or of the order of the wavelength of the incident light, right? So it's important to see the dominant wave effect, that you have the wavelength in the right limit. Otherwise, you won't see the wave nature of this. You will not see interference. That's what it means. Now, here he actually puts down this number. Lambda is h by p, where p is the particle's momentum. So momentum already has mass inbuilt into it, and you can imagine that the more massive the particle becomes, the more large is the momentum and smaller is the wavelength. So imagine that if you want to think of us as quantum particles, then my mass is so huge, my wavelength will be something which is sitting exactly right at the center of my mass, and it doesn't even come out of my body to interfere with somebody else, right? So the point is that it is dominant when your mass is really tiny. So that is why fundamental particles can interfere while large macroscopic objects cannot, because the mass is too large. I hope I could. This is not a very tight answer, not a very correct answer, but it is a reasonable hint towards the answer. Because I can get more technical, but I think I don't think that will help.
That's true. Dr. Ritesh Yadav is here. Dr. Ritesh Yadav. Okay. Yes. Have you any questions regarding this lecture?
Yeah.
Okay. Okay, no questions, I think.
Okay. Then I think no point boring people more with topology and so on, right? That will be just too much. I'll skip that part for now.
Okay,
Yeah.
okay. So, any more questions from participants? If anyone wants to ask any question? Okay.
So audience
So,
are all professors also, right? Audience are all faculty members
yeah,
somewhere.
yeah.
Yeah,
Professors, professors and research scholars.
I see.
But few are research scholars. Most of them are from different assistant professors of different institutes, colleges.
I see. I see.
Okay. So thank you very much, Professor Swarin Das, for your
Thanks
nice
for the invitation.
lecture. Very slant lecture with a lot of informations regarding this topological quantum computing and so. Very nice lecture. So thank you very much. Okay.
Thanks for having me.
See you.
See you then. See you. I'll send the questions. Okay, so by
Yeah.
evening I'll try to send it.
Yeah. Thank you.
Thanks.
Thanks a
Bye
lot.
bye. Yeah. Bye.
Bye. So this is the end of the today's sessions of session 12. In the morning, we can have your because in session 13 morning, maybe I will take your lecture because science and eligibility person is not available since it looks like that is not available. So most probably I will take your lecture in the morning session because you have covered a lot of topics of quantum computing in different aspects, different scenarios, and most important that you have covered a lot of specific topics related to quantum computer or quantum computing. So I will give you some glance of at a glance of all those things, because thereafter you have programming on IBM Composer, that is Qiskit, and that's very interesting. Qiskit is a quantum computing open source software in which Professor S. Sahu of DRDO is expertise. He will demonstrate you how to develop different kind of quantum gates, quantum circuits with the help of this Qiskit software. Okay, so you must join this. And further, we have in the last session tomorrow we have the exam and the valedictory session. That's a very small because exam, and then we have very small valedictory session. So I will send you feedback form that you have to respond and return it by tomorrow. I will send you by mail. That's we require. Any more questions if you want? Okay. So we shall meet you in the morning tomorrow. Okay, fine. Thank you.
Okay, sir. Thank you, sir.